When we think about computing hardware today, our minds immediately go to sleek silicon, right? Tiny microchips, invisible electricity. But what if I told you the blueprint for tomorrow's technology was actually drafted way back in the 19th century? Welcome to this explainer. Today, we're diving straight into Charles Babbage's absolutely wild quest to design the world's very first computing hardware. And get this, he wanted to build it entirely out of brass, steel, and steam. Let's get right into it.
Okay, so to really appreciate what Babbage was trying to design, we kind of have to completely rethink the word computer. See, before machines, a computer wasn't that glowing device sitting on your desk. A computer was actually a human being, literally. Imagine your actual job title was computer. You'd be sitting at a desk doing incredibly complex, super repetitive arithmetic by hand for 8, maybe 10 hours a day. It was incredibly tedious work, and honestly, the worst part, it was highly prone to human error.
Now, what's really interesting about this is the staggering technological leap Babbage was trying to make. He wasn't just trying to build a better calculator. He was conceptualizing the exact same logical operations that we use in modern digital circuits today. But he had to engineer them through physical, moving mechanics. So instead of electrical currents zipping through microscopic silicon, he actually designed physical if-then statements using heavy brass gears, steel cams, and mechanical levers. It's just mind-blowing. So that brings us to a really fundamental question. How do you completely eliminate human error for mathematics? Well, this was Babbage's primary catalyst for invention. Back in the early 19th century, printed mathematical, navigational, and astronomical tables were just absolutely riddled with human typos. And these weren't just harmless little mistakes. Bad math in a navigational table was literally causing shipwrecks and massive financial losses. Babbage realized pretty quickly he had to design a way to take the fallible human mind completely out of the equation.
His solution to all this? It was incredibly audacious. He resolved to build massive, fully automated mechanical engines. And we're not talking about a sophisticated abacus here. His hardware design required a completely automated pipeline to eliminate human fallibility from start to finish. Crucially, the machine didn't just need to compute, it had to automatically print the results too. Because think about it, even with perfect math, humans make typos when transcribing numbers onto paper. So the hardware had to handle the ink as well.
This sheer level of ambition led to his very first major attempt, known as Difference Engine Number 1. It was designed specifically to calculate polynomial functions. But Babbage almost immediately hit a massive wall. His designs required gear-cutting precision that, well, it simply didn't exist in the standard manufacturing techniques of the 1820s. A machine with thousands of imperfect gears isn't going to compute anything. It's just going to grind and jam. And this lack of precision led to some severe engineering disputes with his chief toolmaker, Joseph Clement, which ultimately plagued the whole project.
And as we all know, building experimental hardware is never cheap. The British government actually poured £17,000 into the Difference Engine project. Now, in the 1820s and 30s, that was an absolute fortune. It's basically the equivalent of a massive modern venture capital round today. But as costs continuously escalated and this giant brass machine remained stubbornly incomplete, the government finally just pulled the plug and halted funding. So Difference Engine Number 1 was left unfinished. But here's the thing, rather than just give up, this stalled first engine forced Babbage to completely pivot his design philosophy. He stopped trying to design a machine for a single mathematical problem, and he started designing universal hardware that could perform literally any mathematical calculation as long as it was given the right instructions. It was this exact conceptual leap that ultimately earned him the universally recognized title we know today, the father of the computer. Now, this right here is the absolute aha moment of this explainer. Look at this. Babbage's 1837 analytical engine perfectly mirrors the fundamental architecture of the device you are watching this on right now. No joke. What he called the mill is exactly what we call a CPU, the processing unit. The store, that's your RAM holding variables. He planned to use punched cards for code input and even included a dedicated output unit for printing. He literally designed the exact hardware framework we use today over a century before it was ever electrified. So let's walk through how this physical hardware actually operated in sequence, step by step. Step 1, you input the instructions using punched cards. This was actually a brilliant design choice he borrowed from industrial jacquard weaving looms. Step 2, the variables wait in the store. Step 3, the machine mechanically processes the math inside the mill. And finally, step 4, it prints the results.
I mean, just imagine this for a second. A computer the size of a locomotive, hissing with steam, deafeningly clicking and clacking through these 4 steps just to run a program. It's wild. And because Babbage designed this universal hardware architecture, it opened the door for a brilliant mathematician named Ada Lovelace to actually write the first reprogrammable software. She translated a paper on the analytical engine and added her own extensive notes, which included an algorithm to calculate Bernoulli numbers. So you have this perfect separation. The physical, steam-powered gears were the hardware, and her algorithmic notes were the software. That step-by-step procedure she wrote is widely celebrated today as the world's very first computer program. However, to really understand Babbage, we have to ground this incredible scientific journey in a pretty devastating personal reality. In the year 1827 alone, Charles Babbage lost his father, his beloved wife Georgiana, a newborn son, and another young son. It is honestly hard to even comprehend that level of compounded grief in a single year. Completely devastated, he traveled Europe, isolated himself, and ultimately used his hardware design as an escape. He immersed himself entirely in his mechanical blueprints just to cope. But through that intense isolation, his brilliance as an engineer sharpened immensely. See, his initial concept for difference engine number 1 required a massive, unwieldy 25,000 individual parts. But when he returned to draft plans for difference engine number 2 between 1847 and 1849, he applied all the advanced mechanical layouts he learned from working on the analytical engine. He completely optimized his hardware design, getting it down to just 8,000 parts. He had vastly streamlined his own vision. Sadly, though, his life's work carries a bit of a bitter irony. By 1849, Babbage had complete, highly optimized plans for difference engine number 2, but he just never secured the funding. He died in 1871 at the age of 79, increasingly bitter at a scientific establishment that he felt completely lacked vision. His magnificent engines remained unbuilt until 1991, an incredible 120 years later. That's when the London Science Museum finally set out to build the machine directly from his original blueprints. And what do you think were the results of that 1991 build? Well, 31. To test whether Babbage's designs were actually functionally sound, the Science Museum built it strictly using the 19th century manufacturing tolerances that would have been available in the 1840s. And guess what? The machine worked flawlessly. This absolute masterpiece of mechanical engineering accurately calculated mathematical values up to an astounding 31 digits. It proved, for sure, without a shadow of a doubt, that his Victorian vision wasn't just some fantasy, it was absolutely perfect. Which leaves us with this incredibly provocative question to ponder. If Charles Babbage had the modern manufacturing tools we possess today, what kind of hardware would he have designed? I mean, the guy drafted the exact blueprint of the digital age while living in an era of steam trains and horse-drawn carriages. I really hope this explainer has sparked your curiosity and given you a whole new appreciation for the deep brass and steel roots of the technology sitting in your hands right now. Keep exploring, and I'll chat you next time.